Okay, so the homework question was the half-life of carbon-14 is 5,730 years. I also said in class yesterday that's the only half-life that you have to memorize. Any other half-life I will give to you, okay? But that one you have to know. You have to know the half-life of carbon-14, okay? If you start with 12 grams, how much will be left after 34,380 years? All right? Okay, so the way we're going to do that is following this same pattern in the example that we did in class yesterday. Okay? So I'm going to write HL for half-life. You could write out the words half-life. I'm going to have a row for time. And I'm going to have a row for the amount. Okay? Since this isn't really a table, you can put, like I did yesterday, you can put your units of measurement in the cells. If it was an actual table, you want your units of measurement in a column label, or you could put in a row label. I'm going to put my units of measurement over here in a row label, and the amount is in grams. Okay, so I could just put numbers in the chart. Okay, all right, so in the very beginning, no half-lives have passed, so we've got 0, and the amount, so that's no time has passed. Okay, and the amount we're starting with is 12 grams, and it's 12.00. Okay, and since what we're going to be doing is dividing this by 2 each time, or dividing the amount by 2, then every one of these has to have 4 significant digits. Okay, the reason is I'm dividing by a whole number, and those are counting numbers, and counting numbers don't count for significant digits. Okay, that's the little phrase I use to try and help you remember that. Okay, so for the first half-life, the time that will have passed is 5,730 years. And because I put years over here, I don't have to put it there, but you can put it there. It's okay if you do. But half of this disappears in that half-life. So that's 6.00, but I need 4 significant digits, so it's 6.000. Okay? All right, then. The second half-life, another 5,730 years will pass. So that's 5,730 plus 5,730. So that's 11,460 years. Okay? And the question is, how much is left after 34,380 years? So I'm going to go ahead and fill in this row, just because it makes the math easier for me to do that, because I've got it on my calculator here already. So I'm going to take that 11,460 years and add another 5,730 years. And that gives me 17,190 years. I'm going to add 5,730 years to that, and I get 22,920. Okay, I'm going to add 5,730 years to that. And that's 28,650 years. Okay, and I'm going to add 5,730 to that. And then I get that magic number we're looking for, 34,380 years. Okay? All right. Now each of these is a half-life, so I can just number these 1, 2, 3, 4, 5, 6 half-lives. Okay? And each time I'm gonna cut the previous amount in half. So the next one's gonna be 3.000. And then half of this is 1.500. And 1.500 divided by 2 gives me 0.75, but the calculator doesn't show. I need 2 more digits. Okay, that's how much is left there. And then divide that by 2, and I get 0.3750 grams. Divide that by 2, and I get 0.1875 grams. So the answer to the question is we're going to have 0.1875 grams of carbon-14 left. Okay? All right. So the answer to the question, 0.1875 grams. Okay? Now, we usually put units of species with that too, but the question asks how much of that stuff is left, so you really, it's not wrong if you just put 1,875 grams, okay? If you're showing the math, you have to put what that thing is, okay? If we're doing stoichiometry, for example, okay? All right, our dimensional analysis problems, conversion problems. All right, so this is what I'm looking for here. All this math here, because I want you to show me the math. I'm from Missouri. You're going to show me, okay, this stuff. You look that up. And
You already told me to.
Yeah, I did. That's right.
Did you look it up? Yes, and he's not from Missouri.
All right, never mind. All right, so listen. You have to label the columns or the rows somehow. Okay, you could have done it you can do it vertically too. You don't have to have rows. That's the way I do it. But you could put this as a column label and do everything in a column if you want to, okay? So each of these half-life numbers have to be there somewhere. That's a total of 7 points. 8, well, actually, each one of these rows is 7, okay? All right, so you got a total of 21 points for this work. Do what now? No. If you just show me the work, I'll accept that as being the final thing there, okay?
So we have to have it set up like that?
Huh?
We have to have it set up like that?
No, but you have to have all the numbers organized somehow. You know, if you want to organize as in columns instead of rows, you can do that, okay? But you have to show me the work, all right? That doesn't mean you have to show me the math necessarily, but you have to put the work in, the numbers in here, okay? Anybody have any questions about that? All right. So make sure the points are on the paper where it belongs. Okay, make sure your name is on the paper you're evaluating where that belongs. Okay? Really? Okay. All right, listen. Listen. I'm just sort of taking a minute here and scanning through everything. I need to change this. I'm looking at the compiled notes I have for this unit. If you go through the compiled notes that I put on Google Classroom for you, there's a section here on quantum numbers. We don't teach quantum numbers in this class anymore, so ignore quantum numbers. But I think everything else in there pretty much is covered, okay? So regions of the periodic table, orbital notation you're asking about, electron configurations, ion symbols. Did we cover electron dot notation in here? Yeah, okay. Yeah. Those balloon models where we learned about the shape of the actual orbitals themselves. Okay, you have a review day, just be patient, okay? I'm trying to go through all this. All right, there are two things we need to cover today. One of them is a little more information about nuclear stuff. Well, actually, both these things are nuclear stuff, okay? We have talked about nuclear decay. There are two other nuclear processes besides nuclear decay, okay? One is nuclear fission, Fission, nuclear fission, all right? And nuclear fusion.
That's almost the same word.
Almost. Okay? Well, you can get explosions from either one. Okay? Not nuclear.
Why not?
Okay. Shh. Nope, the closest thing we come to that is nuclear decay, where you got a chance to see evidence of nuclear decay yesterday.
Got you.
Okay, radiation you saw yesterday, or evidence of that safe radiation yesterday. All right?
My fingers have been glowing in the dark.
I doubt it. Okay, there was some gamma radiation. Yeah, but there's gamma radiation everywhere. Okay, there's gamma radiation in this room right now. Guys, listen. Human bodies are designed to absorb without any ill effects a certain amount of what could be dangerous radiation. I mean, you go out in the sun and you need a certain amount of sun. Okay, it create, what is it? You need a certain amount of sunlight. What does it make? I forget what it is. What? Yeah, that's it. Okay, shh, guys, shh. But too much sun, and particularly that wavelength you can't see, ultraviolet, you get sunburn. Okay, that's not good. Yeah, okay. But listen, please. Shh, listen, please. There are other forms of radiation that are even more potentially dangerous. Okay, X-rays. When you go to the dentist and they take pictures of your teeth with X-rays, they put a lead apron over you, and the X-ray technician steps out of the room.
Yeah, I feel like that.
Yeah, they're like, I mean, it's all you, but.
That's right, because they are working with that stuff every day, where you only get it, once a year or whatever it is. Okay. Huh? Okay, 6 months. All right. So, yes.
How do things glow in the dark?
Okay, that's another process. Hold that question for a second. I'll come back to that. Okay. Gamma radiation is present everywhere. You cannot get away from gamma radiation. It's in this room right now. Your body's designed to handle a certain amount of gamma radiation, but too much can make you very sick and can kill you. Okay? Yeah, you're supposed to turn your phone off.
It is off, but
Okay, all right. Shh, look, guys, pay attention, please. Okay?
I think that's when it's off of the class.
Okay, look, let's don't go there. Let's stay focused on the content, okay? Gamma radiation is everywhere. Your body's designed to handle that. Too much gamma radiation and you might become the Hulk, maybe. No, you won't be. It'll kill you, all right? And radiation sickness is a very nasty way to die. Okay, you don't want that. Okay? Shh. So, the small amount of gamma radiation yesterday is less than the radiation you're getting from the concrete walls in this building every day. Okay? So there's no danger from the radiation that you experienced with those little tiny rocks of low-grade uranium ore. Got it? So it's just like a lot of things. Your body is designed to handle a certain amount of chemicals that in higher doses would kill you. Okay, if you like almonds, you are eating cyanide every time you eat an almond. Cyanide is rat poison. Too much cyanide, you die. Okay? Shh, guys. So, a lot of nuts have cyanide, but almond has a lot of them. Okay? The smell of almonds is the smell of cyanide. And the thing is, the sensory nodes in your nose can't tell when there's a lot or little. So there might be enough cyanide in the air to kill you, and you wouldn't be able to tell because it just smells like almonds. You know, it's not an excess amount. Okay? All right, let's go back to fission and fusion now.
Wait, so can you like die from eating too many?
You can die from too much water. Okay?
Well, that's true. Isn't it like it's even if you slow cook kidney beans, like, isn't that really bad?
What?
If you like, it's like I think it's kidney beans. You're supposed to cook them like you can't put them in a slow cooker because then they're like poison.
No.
I don't know.
I make chili every Super Bowl weekend, and I cook it for a long time. Huh?
Do you get them out of can?
Yeah.
Yeah, I think like if you cook them like from raw.
No.
I don't know.
No. Shh, shh, shh. There are certain tubers that are poisonous if you don't cook them. Okay. Huh? Tubers like potatoes. Okay. Shh. Anyway, let's don't go there. Let's stay with this stuff. All right, right now. All right, fission. Fission. The word itself means splitting. Okay. Yes. Means splitting. All right. So fission, if we're talking about nuclear fission, it means splitting the nucleus. You have to have a large and unstable isotope or nucleus, a large and unstable nucleus for fission to occur. It doesn't just happen, pretty much on its own. You can dig all the uranium you want to out of the ground, and even the uranium coming out of the ground won't, or very rarely on its own, will go through fission. And there's not enough there to cause any problem, not as far as fission is concerned. Okay, you have to enrich the uranium to get the kind of fission that creates a bomb or a nuclear power plant. By enriching, what I mean is most of the uranium in the ground is uranium-238. The vast majority of the uranium that comes out of the ground is 238. That's what was in that sample you had yesterday. Okay? 238 doesn't go through fission. Uranium-235, a more unstable isotope of uranium, does go through fission, but you have to pretty much initiate the fission. It just doesn't do it on its own. Some of it will, but unless you enrich the uranium, that is to say, increase the percentage of 235 so that the decay products can, one strikes another, you don't get that chain reaction to cause a nuclear reaction that we can create heat in a nuclear power plant or a bomb. Okay?
You change it from like 238 to 235?
You don't change it, no. In a sample of uranium dig out of the ground is a very small percentage of uranium-235. Okay? And what they have to do to process the uranium to use in a nuclear power plant or in a bomb is they have to get rid of a lot of the 238 and keep a lot of the 235. Okay? So when we are worried about Iran making uranium from which they can build bombs, we're worried about them enriching the uranium enough to make bombs.
We should just put them in a big baseball box.
Huh?
You gotta put them in a big baseball box.
Well, it's more complex than that. What? Okay. So, fission works like this. Here's a large nucleus. Okay, a large and unstable nucleus. Now, we think about nuclei of atoms as being hard kernels, like the seeds in an apple or something, or in an orange or something, okay? But the nucleus itself is not just sitting still. It's wiggling and twisting, okay? It's kind of like a big blob of jello when it's big like this, okay? Like you had a baseball-sized glob of Jell-O, you threw it through the air. If you could slow motion it, it would be wiggling and twisting around. All right. So if this were, say, for example, uranium-235, that in itself would probably go through nuclear decay. It wouldn't go through fission. What you do to make it go through fission is to attach an extra neutron. Okay?
So is this what Einstein was doing?
Huh?
Is this what Einstein was doing? He made bombs?
Well, Einstein didn't himself make bombs.
You like came up with.
Einstein was on the team that helped design the bomb,
Gotcha.
the first atomic bomb.
He had locked himself in his room for like a month after he did it because he was mad.
I don't know that. I don't know that. Yes. What? It's another neutron. Okay? Now what that does then is make uranium-235 into uranium-236. Uranium-236 doesn't exist in nature, but in this process we're creating an even more unstable isotope that will spontaneously go through fission.
Now that's great for bombs.
That's great for bombs. Okay? All right.
Wait, so how do you make a bomb?
Not great for China.
You know it's not great for China?
Okay, please pay attention. Now, when you do that, when you create uranium-236, and that's a very temporary, it doesn't last very long at all because it breaks up automatically. Okay, it's spontaneous. It splits into large chunks. And there's several different types of chunks it can split into. I'm going to just give you one example. Okay, one of the sets of chunks you can get from this is barium-143. And krypton 91. Okay. All right, so we've got 235 plus a neutron creating 236, a mass of 236. Add 143 and 91 together.
That's not right.
It doesn't come out right, does it? Okay? So what's happening here is not only are we getting two big chunks, we're getting some crumbs. A couple of extra neutrons. Now the math works out. Okay? Well, those two neutrons then can go along and latch onto another uranium-235, and that splits. And those create more neutrons. And some of these decay products give you 3 and 5 neutrons. Okay? And so this, if you have this cycle continuing, and it happens really, really fast, you have what's called a chain reaction. If you have a chain reaction, you have what's necessary to create enough heat to power a nuclear power plant. Okay? If you were to cause it to happen fast enough, you'd have enough reaction to create a bomb. Okay? Now, the bombs that were created at the end of World War II, this didn't happen unless you had explosives, chemical explosives, that bombarded it from all sides almost simultaneously. It's actually a series, okay? But you have to initiate the nuclear reaction with a chemical explosive to get a nuclear bomb or an atomic bomb.
Wait, what happened to Chernobyl?
Huh?
What happened to Chernobyl?
Chernobyl was a meltdown. Chernobyl happened, and 3 Mile Island was a meltdown. Okay? Fukushima was a meltdown. All right? So what happened is this kind of reactions like this are taking place in a nuclear power plant in those cases. But the ability to be able to control it was lost. So with Chernobyl, I think the coolant system failed. I'm not sure. But you have to constantly cool the reaction. You have to have the rods that contain the uranium are kept inside. Most of the time, it's carbon, it's graphite, and it absorbs some of. And so you keep the neutrons from going along and hitting other uranium-235. You control how fast the reaction occurs. If the process of being able to raise or lower those rods fails, then the reaction gets out of control. And that happened at 3 Mile Island in the United States. It happened at Chernobyl in Russia. It happened at Fukushima after the earthquake and the tidal wave that resulted from that. Okay? So that's a chain reaction. That is fission. That make sense? Yes? Okay? All right. That's fission. Now, fusion then is when you take much smaller particles and stick them together. If you break a bone and they put you in a cast, then they're setting that bone so it doesn't wiggle around and allows the bone to fuse back together. Okay, the biological processes in your body cause the bone to actually knit back together. Okay, that's fusion. All right,
So we're putting like pieces of like the nucleus together.
you're putting them together. That's what happens in the sun. Okay. Now we don't have the ability to do fusion on a large enough scale to create power. We can create bombs with it. Okay, we can't control it well enough to be able to create power with fusion. If we were, that's kind of like the holy grail of nuclear physics these days. Okay, trying to find a way to be able to do that. The problem is the pressure and heat so high, we don't have a vessel we can put it in to keep it under control.
Put it underground, and then if it blows up, nobody's hurt.
Well, they have set off nuclear bombs underground, but we don't have a way to control it even underground. Okay? Huh?
Just a big hole under, like, just falling.
Right. Okay. Yeah, that sounds nice. That sounds easy, but it doesn't work that way. Okay? All right. So, if we're going to do fusion, you might have something like one of the isotopes of hydrogen. Okay? So, this hydrogen isotope has 1 proton and 1 neutron, so it has a mass of 2. It has a special name. This is called deuterium. Okay? And if we were to fuse that together with another isotope of hydrogen, okay, Marvel Comics fans, this is what Dr. Octopus wanted to power his fusion reaction. Well, he didn't fail, but the process failed eventually because, Spider-Man took him on.
Dr. Octopus was for like 30 seconds. Yeah, I remember.
Okay.
Like a lame.
Yes. I'm sorry, I can't hear you over our young man over here that can't seem to keep his mouth quiet enough for me to hear other people. What? What now? This says deuterium, and this says tritium. Okay, these isotopes are important enough that we have special names for them. Okay, and both of these exist in the center of the sun. Actually, it's a cycle that goes through. So there's this cycle of fission, fusion processes that take place until you end up with the last stage in the process, where deuterium is combined with tritium in a fusion reaction to create a form of hydrogen. A form of helium. Okay. Now, there's actually remember we said here we make 236, uranium-236 that actually breaks up into this, and that's a temporary form. There's also a temporary form in between here and the actual final products that's very, very unstable. but after you make that unstable product, it then decays so that we get a final product of helium. So when you hear or read stories or whatever about hydrogen fusion creating helium, you actually have an intermediate step in there. We don't really ignore it, but you need to know that it's part of the process, okay? And so we end up with an extra neutron in the process, okay?
So we can make helium?
Huh?
So we can make helium?
We can make it, but we can't control a fission reaction on a scale large enough to make this practical.
Okay.
But if we were to use, now this creates a pile of power, okay, way more power than you create with this, all right? If we were able to get this to work and well, what was that series of movies, Back to the Future, okay? If you could do that,
We can go back to the future.
well, that's a movie, okay? It's like Spider-Man, doesn't really exist, okay? Not right now, anyway. All right, shh, please, okay? And so, the byproduct of this reaction, relatively safe stuff. Now, here's what you need to know about the safe part of this. The radioactive byproducts of this, the radioactive leftovers of fission, are dangerous, read deadly, gamma radiation, for hundreds of thousands of years. Okay? The radioactive byproducts or waste products of this reaction are dangerous, think deadly.
Is that what that elephant was? What's it called in Chernobyl? It's like a big thing, glows. It's called elephant split or something.
I'm not sure about that. I don't know. Chernobyl's gone through a couple of stages of mitigation. Okay, the first thing they did was just to pour a bunch of concrete on top of it. But all the heat of the leftovers decaying basically chewed up that concrete.
They have like a metal dome over it now.
Now they have a metal dome over it. So they built a metal dome off to the side and kind of rolled it up on top of it. Okay, it's not a dome. It's kind of a Quonset hut shape. What?
It was a power plant and it kind of blew up.
Yes. Well, it didn't blow up. Okay. Yeah. Killed a lot of people.
Can you take boards there now?
Huh?
That's kind of dumb.
All right. Let's. All right. Now we can't do fusion right now, but if we were able to do fusion, the byproducts would be much. What we think would be much safer.
You would just talk about it.
Well, okay. And the helium that we have on the planet Earth is a finite resource.
Isn't it aren't we running out of it?
Yes, we're running out of it. The largest helium reserves in the world are in the United States. And we're using it up to make balloons. Okay?
Is there something else we could use to make balloons that's as cheap?
Not that safe. Not that does the same thing. Okay? Yeah, hydrogen explodes. That's not good. That's like, what was the dirigibles, right?
Balloon that exploded?
Yeah. Yeah, that wasn't a balloon
It was
because it was rigid. That's why we call it a dirigible. Okay? Yeah, the one that burned over in New York State, New Jersey, somewhere up there.
Really is, actually.
kind of like a sky hotel or something.
Okay. All right. So fusion and fission. Now, some of those equations that we did on that worksheet were fusion and fission equations. Okay, let's see if I can pull that up. So this would have been a fusion reaction here. We fused, well, theoretically speaking, we fused nitrogen and helium together to make oxygen and a leftover hydrogen. Okay? Let's see, this would have been a fission reaction, And the two bombs that were made to close out World War II, one was a uranium bomb and one was a plutonium bomb. So this is the reaction that, or a reaction like this, one of many, would have taken place in the Hiroshima bomb. Or the Nagasaki, I can't remember now which one was which. Let's see. Here's the kind of reaction we're talking about here when we're just talking about that happens in the sun. The fusion reaction in the sun, okay? We'd like to be able to do, but we can't right now, so, okay? All right, so that's fusion and fission. Now, we've talked about stable isotopes, and I want to dig into stable isotopes a little bit further, but I want to go back just a little bit to carbon-14, okay? The reason that you have to memorize this number for the half-life of carbon-14 is this. Carbon-14 is the basis of one of the most important ways we date things. I don't mean we go out on Saturday night and date, okay? Carbon-14 is the substance that helps us figure out how long something's been dead,
Oh, yeah.
okay? It's called carbon dating.
That's how they feel like how like rocks are and stuff.
Not rocks.
I knew
Rocks you can't use carbon dating for. It has to be something that was alive, like dead people, like the mastodons they found in the frozen tundra, when it's melted, partly melted, okay? Mastodons, huh? So it has to be something organic, and the organic still has to be there, okay? So it's not truly a fossil. A fossil is evidence that something was alive, but the original stuff isn't there anymore, okay? So this is the process of carbon-14 decay. And what you do is there is a certain amount of carbon-14 in the air. As long as you are alive, as long as plants live, as long as anything is alive, it's ingesting carbon-14 along with all the other things you breathe. It's part of the carbon dioxide in the air, okay? And so the percentage of carbon-14 in your body stays relatively consistent as long as you're alive. Once you die, then you're not ingesting carbon-14 anymore, and it starts to decay. So if you figure out how much carbon-14 is left, we can figure out how long you've been dead. Okay?
Well, like, is there a point? Well, no, it'll never be zero, will it? 'Cause it's half-life.
Never be zero. Now, carbon-14 has, there's an outside limit, okay? The further back you go, the more error there is possibly. So if we say something's been dead for 20,000 years, that's plus or minus 1,000 years or something, okay? But if we're going back 500 years, we can get pretty close to that, within a few years, all right? So it really kind of depends. And so we've compared the amount of carbon-14 to the amount of nitrogen-14 in these organic materials.
There's no way to, like, preserve that?
Huh?
There's no way to preserve it?
What do you mean?
So there's no way to, like, falsely, like, make it, like, not, I don't know how to explain it. There's no way
Keep this decay process from happening? No. It's happening all the time, okay? So you can date things, but you gotta, eliminate all the other things that kind of get in the way and stuff like that. Like, if you're trying to date the Shroud of Turin, well, you got all this stuff that's been contaminating the sample, so you can't always correctly do that. It becomes a problem, okay? So things that are buried underneath the ground, well, you kind of eliminate some of the contamination, so that works out a lot better, okay? All right, so that's, those are things you need to know. You need to know the half-life of carbon-14, you need to know carbon-14 is how we do carbon dating and what it's used for, okay? Now, there's other forms of dating used for rocks, so we can use other isotopes of elements to find the dates of rocks, for example.
But aren't all rocks, like, old? Like, as old as Earth? How long do you know how old a rock is?
Well, there's a phrase called old as dirt, okay? Yeah, they're all old, and these processes we use for dating strata underneath the earth, okay? That uses, substances that have a much longer half-life than carbon-14. Okay?
You know what I found? Like, I found out like last week.
All right.
That's how it happened. Like, something hit that. Like, it made them move.
Okay, now, stable isotopes, stable isotopes, stable isotopes.
Carbon-14.
The nucleus of an atom is made of neutrons and protons. Neutrons and protons are, we have this term for those, they're called nucleons, okay? So a neutron's a nucleon, a proton's a nucleon. The things that are in the nucleus are, the larger particles in the nucleus are called nucleons, okay? In smaller nucleons, where you have up to 20 protons, you need roughly an equal number of neutrons and protons to keep that nucleon stable. So that isotope is stable if you have roughly the same number of neutrons and protons. The larger the atom gets, though, the larger the nucleus gets, the higher the percentage of neutrons that are needed to keep the nucleus stable. So past element, the element that has a proton number of 20, past that, an equal number of protons and neutrons no longer gets it. Stable isotopes have to have increasing percentages of neutrons to keep the nucleus stable. Okay? And then once you get to element 82, what's that? Element 82? That is a great question, and where would you find that answer? That's exactly right. Okay?
I'll find it, don't worry.
Well, somebody's already answered it, but please do. Yeah, lead. Okay, good. Lead, just hold on to it for now. Okay? The largest element, the element that has the highest proton number or atomic number with a stable isotope is lead. So every isotope of bismuth, the next element, every isotope of bismuth, every form of bismuth, and every element past that, none of those isotopes are stable. Now, what does stable mean? Stable means it doesn't go through decay. Unstable means it does go through decay. So every element, beginning with bismuth and on up, all the forms of that element are radioactive. Okay? Now, bismuth is very stable. The most stable isotope of bismuth has a half-life that is longer than what we believe to be the age of the universe. Okay, that's pretty stable, but it's still radioactive. It goes through decay. Okay? So, all the stable isotopes are between element number 1, or begin with element number 1 and end with element number 92. Got that? All right. When we first started talking about graphs in here, I said that when we do labs, every graph we will create has an independent variable, because that's the reason for doing the graph in a lab. This graph does not have an independent variable. If we're doing a graph in a lab, then there's a way to write titles, and the titles tell you when you read it what the independent variable are. We write it in the form, the effect of independent variable on the dependent variable. This graph we're going to do here does not have an independent variable, so we're not going to write a title in that format. Does that make sense? Okay. This graph you can simply call, we're going to give it a title and a subtitle. The main title is the band of stability. The band of stability. Band of stability.
Yeah, that's the title.
That's the title, the band of stability. Huh? Yes, you can do it in pencil. In fact, I'd recommend you do it in pencil.
Which way
the way that I've got it on the screen here. All right, so the narrow side is over on the right-hand side, so you got plenty of room to put your labels over here and down here and the title up here, okay?
The band,
Of stability. Okay, so the subtitle we're gonna put on this is a comparison. A comparison.
That would go underneath.
Yeah, go underneath. A comparison of the number of protons and number of neutrons for all the stable isotopes. That's the subtitle.
Run that over one more time.
A comparison of all of the protons and neutrons in all the stable isotopes.
so would you put the band of stability and then comparison right under it?
Yep, that'd be the subtitle. Okay?
All stable elements?
Yep, of all the stable of all the stable isotopes. You could say elements, but the thing is, we're talking about different forms of these elements. Isotopes. Yep. Okay. All right. Now look, if you're talking about other things and I'm trying to explain things, and then you ask me to repeat myself, I kind of get frustrated. Okay? Can you imagine? Okay? All right. Well, I'm glad. Then I feel you there. Okay? All right, good. All right. So, we're going to put the number of protons on the horizontal axis. We're going to put the number of protons on the horizontal axis. And we're going to put the number of neutrons on the vertical axis. The number of protons on the horizontal axis, the number of neutrons on the vertical axis. Okay. Now, something that a lot of students apparently don't realize, and you need to know this, all the graphs we do at the high school level have to have evenly spaced number lines. Okay, I mean, I have people do graphs where this is like a 3, and that's an 8, this is a 4, and that's not the way it works. Evenly, I know that doesn't make sense, does it? But that's, people do that because they don't really realize, oh, it's supposed to be an even numbered number line. Okay, so what's on the horizontal axis is a number line. What's on the vertical axis is a number line that's evenly spaced. Got it? Okay, this is for stable isotopes. I've already told you something about stable isotopes. I said beyond a certain point, there are no stable isotopes anymore. What was that point?
82 after the.
After lead, there's no stable isotopes anymore, okay? So, we need to, because in all graphs, even when we do it in the lab, you need to spread the data out to try and cover as much of the available space on the graph as possible so it's easiest to tell what the pattern is. That makes sense? So get with somebody near you and figure out horizontally where the protons are going to go, how you're going to space out this number line so you have an even spacing as wide as possible. That make sense? Go. Yes. Protons on the horizontal axis, you're going to turn it this way. Protons, neutrons. Right now we're just worried about protons. Yeah, I kind of made this way too easy for you, didn't I?
Yeah. Probably 1 through 10.
So if we make this 0 here and this 10, 20, 30, but I'm doing this exercise and asking you to do that because I want you to think about graphs where your number lines have to be evenly spaced and your data needs to be spread out as far as possible. If your data points are all kind of grouped together in a little corner down here, that's not spread out, okay? All right? And that'd be, I mean, we could spread it out more than that, but that would require more math. It's really, it's kind of unnecessary, okay? All right. And then we're going to put neutrons over here.
Well, then, I guess it's just technically known by 2.
All right, now let me tell you about neutrons. I need to have 1.5 times more neutrons than protons.
It's already, I think it's already about 1.5 times longer. You could still go by 10, but it's longer.
Really?
Than,
Well, check it out and see. Check it out and see.
Or 20s.
Check it out and see. 1.5 more times more neutrons than protons. Okay, so if you thought this through the way that I've asked you to do that, you should have a numbering system that looks like mine. Okay? Okay. Now listen. Listen. This band of stability that you're going to do is not the actual band of stability, because that would be plotting individual numbers for 118 elements. Well, I'm sorry, 82 elements and all these different isotopes that are stable. Okay? We're going to have just sort of a general representation here. But it's going to help you, I hope, to understand about proton and neutron ratio for those isotopes that are stable. Okay? Guys? All right. You need 4 guidelines for doing this stable isotope plotting. Okay? You need a guideline where protons equals 20. So just put a guideline on here where protons equals 20. You can put a dotted line with your pencil.
well, you can't see the dotted line because it's on a line.
The third guideline needs to be a guideline where protons equals neutrons. Listen, be careful. You don't just draw a line on here and hope it is protons. You got to actually plot it and make sure that protons equals neutrons on whatever your graph paper is.